Okay, today is day 3 for us. Going through early Math 141 material, which is not calculus yet. Hopefully it's review, pre-calculus. I want to give you a chance, as I mentioned earlier, at the end of class today, for those of you that are here in class, to ask questions over the first 2 sections, the last 5 minutes or so, maybe more. We'll see how it goes. As well as those that are taking this course via cable, and those that take it later. You can see some problems being worked out, maybe you have questions about too. The topics today are here on the screen for you. This is section 3 in the text. We're going to kind of work with some old friends, some old functions that we're supposedly familiar with, all lines, y equals x squared, y equals square root of x, parts of circles that we know the general equation, x squared plus y squared equals something squared. So when we say from old functions, those are functions hopefully that we know something about. We know where they are, we know where they start, we know how they progress in the plane. And now we want to do some shifting of those. These are some things that are in your book, and I'm hoping that as we go through this in section 3 that it rings a bell. And I want to kind of go back to something that hopefully the bell is ringing, but maybe we're not quite sure why it's ringing in the way that it's ringing, why we're shifting right when we're subtracting C, and why we're shifting left when we're adding C. I might need some of your help on that. I think the easier two are the two at the top. These are vertical and horizontal shifts. So if we want to shift upward, we'll simply tack a constant on to the end of a function. So if we have a function that we know something about, and that's what we're talking about, old functions, y equals x squared, that if we want to make a shift in that, we can basically take every y value. I mean, if you compare this to this, the y values here are x squared, the y values here are x squared plus 4. We've simply added 4 to every y value. And if you think about what you're going to do with that, you take every point and lift it up 4 units. So this takes our old friend and raises every point up 4 units. So, and I'm not going to do this with every one of them, but we can do it with the first one. If this is y equals x squared, then y equals x squared plus 4 would look like that. So I think this is stuff we're familiar with. If we see y equals x squared minus 3, we would expect every y value to be lowered by 3. So that net effect is to move this graph down here. The vertex is the easiest point to work with. And we'll take it, same shape, just translate it or shift it downward in the plane 3 units. So that's the first two. Distance of C units upward, distance of C units downward. That's old stuff, I hope. If we have the function of x minus C, we want to shift the graph C units to the right. Now that may not seem right, other than the fact that you have that committed to memory from some previous math course. So why, if this is our old friend, what about that? Well, according to this review area here, the fact that we've subtracted 2 from every x value before we square it has the net effect of shifting it, what's it say? Right 2 units. Now why is that? Why would subtraction of 2, and I don't want to belabor any of these points, but we can at least get this one. Why would subtraction of 2 have the net effect of shifting everything to the right 2 units? What do you think?
Because the equation already starts off with the negative sign, so the number you plug in will be a positive one. So it goes right.
Okay, give me an example of what you're saying there. Because that may be
Like,
what I'm looking for, but
if you plug in 3, it'd be x minus 3, whatever, squared. Or if you plug in negative 3, it'd be x plus 3. Because there'd be already a negative sign there in the equation. It's double negative.
okay. So then why would that force the graph to end up shifting right 2 units, Tiffany?
If you take the equation, x minus 2 and set it equal to 0, and x equals 2, so it'll be positive. So
Okay,
it'll be on.
there's a point, okay, and maybe that's what you're getting at right there with the negatives and negatives. So here, this one is at when x is 0, y is 0, right? Now, if we want to get 0 out of this, we've got to plug in what? 2, 0, so we're sliding the vertex over 2 units, right? Well, let's take that issue, that when we put in 0, it gives us the y value 0 here, and 2 gives us the y value here. So we're kind of at the same y value 2 units later. Does that make sense? 2 units further, and when we go further, don't we move to the right? Later, further, all those end up going to the right as we move from left to right on the number line. So by subtracting of 2, we cause things to happen a little bit later, while later graphically is right. Does that make sense? So here's our old friend again. And this one, by subtracting of 2 from every x value prior to squaring it, and you could make a table of values to validate this. Same shape, 2 units further to the right. So if this causes things to happen a little bit slower because we're subtracting, by adding things should happen a little bit faster. Well, what's faster mean graphically? In a left to right mentality, if things happen faster, they happen further left, right? Correct? I guess I should say right after that. So if we have this, by adding 3 prior to x, prior to squaring this quantity, then we ought to be able to get to the values we would have gotten to earlier, which is left. So we ought to have the same parabola over here, and you can use that same thought that Tiffany gave us a minute ago. X has got to be 2 to give us 0 here, well, x has got to be what? Negative 3 to give us 0. So we've got that same parabola. Opening upward, just shifted left 3. So those, I hope, the top ones there are very much review. The ones on the bottom, reflecting, stretching, compressing. We've seen a little bit of that in here at this point, so let's pursue that a little bit as well. Let's not stay with the same function. In fact, I'd like to move, since we're going to get a good dose of trigonometry in here, let's go on to some trigonometric functions. Y equals sine of x. And let's say we put a 2 out in front. Everybody pretty comfortable with what sine looks like? Oscillatory function, right? Mm-hmm. Period of what?
2 pi.
2 pi, so it repeats itself every 2 pi. No matter what block of 2 pi you look at, it's repetitive. What's the amplitude?
1.
1, which means it oscillates a total of 1 unit, right? Away from, in this case, the x-axis. So if we take 2 sine of x, what have we done to that?
Made the amplitude more?
Okay, the amplitude is now doubled, right? Because what's the most we could ever get out of this that I'm putting in brackets? The most you could ever get out of this is 1, right? The sine of something at most is 1. Now we're going to double that. What's the least you could ever get out of this? Negative 1, right? And now we're going to double that. So it's going to go, instead of going from 1 to negative 1, its amplitude is now doubled up to 2 and down to negative 2. Does the 2 out in front change the period? Does not change the period, because the sine of x still has a period of 2 pi. We're just going to go up a little higher and down a little lower, but the period is still the same. So if sine of x looks like this, then we should expect 2 sine of x. Twice 0 is still 0. Twice 1 is now 2. Twice 0 is still 0. Twice negative 1 is now negative 2. Twice 0 is still 0. So we're not going to change where it hits the axis, thus we're not going to change the period, but we are going to change the amplitude. So here the amplitude is 1, the period is 2 pi. Here the amplitude is 2, period is still 2 pi. Now that's not the whole graph, so we hopefully know that this thing repeats down here, and same thing with this guy, right? So we can take a look at any block of 2 pi and we can see either one of these pictures. Okay, how is it that we change the, let me leave that one up there. How is it that we change the period? I want to compress this thing. What can I do there? I want the period to be cut in half. Period is 2 pi here. I want my new one to have a period of pi. 1/2 sine of x? Okay, what, now let's take that thought. What's 1/2 sine of x? What's that going to do? That will vertically, 0, half of 0, 0, half of 1 is now a half. Right? Won't that kind of squeeze it down a little bit that way? Still changes the amplitude. So that number out in front is going to change the amplitude. I want to change the period. I want to cut the period in half.
Multiply x by 2.
Multiply x by 2. Now let's see if that has a chance of working. If we double the angle, aren't we going to cause things to happen faster? Right? It's not going to take a full 2 pi for it to go through its cycle. It's now going to happen in half as much space. So by doubling x before we take the sine, I mean, let's examine this. This is still the sine of something. It doesn't matter what it is. Isn't the sine of something limited from 1 to negative 1? Right? Same as over there. Sine of x was limited between 1 and negative 1. Here's the sine of something. The sine of anything is bounded between 1 and negative 1. We're just doubling the pace here. Things are going to happen quicker, which has the net effect of kind of compressing it. Now, if that still doesn't seem right to you here, make yourself a little table of values. And let's see what we get here. What's the first thing we do when we're plotting points on this one? Double the x value, right? Then take the sine. So we double 0, still 0. The sine of 0 is 0. That can't tell much from that. Pi over 6 doubled is pi over 3. What's the sine of pi over 3? That's the equivalent of 60 degrees. Appendix C in the back of the book for trigonometry review. What is it?
1/2.
1/2? Sine of the equivalent of 60 degrees. Right? This is the equivalent of 30, right? Degree equivalent of 30. Square root of 3 over 2? About 0.866. Now, if this were really pi over 6, instead of doubling pi over 6, what would the sine of pi over 6 be? That would be a half, right? So things are happening a little more quickly here. Pi over 4 doubled. 2 pi over 4 or pi over 2. What's the sign of pi over 2?
Square root of 2 over 2. Square root of 2 over 2.
Pi over 2, sign of the equivalent of 90 degrees? 1,
Oh.
1.
right? Pi over 3 doubled is 2 pi over 3. That's the degree equivalent of 120. I'm glad I chose sine. Get a little sine review here. What's the sign of 2 pi over 3?
Square root of 3 over 2.
Square root of 3 over 2 again?
Mm-hmm.
And pi doubled, that's 2 pi. What's the sign of 2 pi? 0? Now, did we ever go above 1? Never went above 1. And we're not going to because this is a sign of something. Let's see here. Pi over 2. Let me make this a little better here. Go with pi. Pi over 2. I don't want this. That's what's wrong here. I don't want pi. I want to go from 0, 30, 45, 60, 90. That's what I want. That's what I was wondering what in the world happened there. We left some out. It's not going to change the result. Pi over 2 doubled is pi. Sine of pi is 0. But I was looking at this being done at pi. I didn't want that. I wanted that to be done at pi over 2. Okay, 0, we're at 0. Pi over 6, we're at this value. Pi over 4, we're at 1. Pi over 3, we're back at that value. And pi over 2, we're back down here to 0. Now that's kind of a typical sine, positive sine wave. Normally, how long does it take for that to happen? Normally that takes place in the first pi, right? And then the negative piece takes place in the next pi. Well, we're done with the whole positive piece in pi over 2. How long is it going to take for the whole negative piece? Another pi over 2, right? So we're going to be done with this sine shape in pi. So the period of this one, amplitude is still 1, period is pi. So would you say that putting the number 2 in front of the angle, doubling the angle prior to us taking the sine, affects the period inversely? Is that a legitimate statement?
Yeah.
Right? So doubling caused us to divide the period by 2. So is that, you've seen that before? Doubling and tripling the angle, compressing or condensing the graph, because normally a sine graph would look like this, right? So we've compressed it in this fashion to get this. So there's a variety of ways that we can alter graphs, compress them. You can do a bunch of things simultaneously on functions. Probably ought to take a look at one of those before we leave this. That's too much, isn't it, in one? Nah, we can handle that. Let's see if we can predict ahead of time how our old friend, just y equals sine of x, gets altered by this. Matt?
Do you want us to guess?
Yeah. Intelligent
Amplitude.
guesses.
It'll stretch vertically, it'll 3 and negative 3.
Okay. So that's going to affect the amplitude and basically stretch it, as Matt said, right? Up to 3 and down to negative 3. Seems like we have agreement in here. Okay, what else?
It's gonna compress the period.
Okay, the 2 is going to compress the period because we're, instead of doing something here with the angle by itself, we're doubling that. So it's going to affect the period inversely, cut the period in half. Now there's a new one. No, it's not a new one.
Move it to the right.
Okay, there we go. We've already seen that, haven't we? That instead of x, we've got x minus pi over 4. So that is going to shift things right pi over 4, right? So can we do all 3 of those? We can do all 3 of those. Now this is typically called what? Remember what that's called?
Phase shift.
Phase shift. Hopefully that rings a bell. So we've got a phase shift to the right, or just positive pi over 4, where period is cut in half by this coefficient 2, and the amplitude has been tripled. Gosh, how would you go about sketching that with all 3 of those? I think I know what I would do. I would probably graph this and this first. I think I can handle those 2, and then just slide some points over to the right, pi over 4. Here's probably how I would handle this. So amplitude is 3. Let me plan ahead here. The period has been cut in half, so we're going to be finished at pi. So we'll be halfway done at pi over 2. So if I just graph that, I think I can handle those 2. Then I know I'm going to climb up here to 3, be halfway done at pi over 2. This is a sketch, by the way, not a graph. Does that seem to do what it's supposed to do here? Amplitude of 3, up to 3, down to negative 3. We doubled the angle prior to taking its sine, which should cut the period in half. Should be done with a full sine cycle by pi. Okay, now I want to institute this phase shift of shifting points over to the right, pi over 4. Let's take this point, move it over here to the right. Take this point, move it over here to the right, pi over 4, this point, this point, and this point. So if this is pi over 2, this distance, then half of that is pi over 4. So that ought to be our final graph, or sketch anyway. That's a rough sketch of where it is in the plane. Now, how much of these should you sketch or graph when you're doing that? 1 full cycle. Just graph it through a full cycle, and that's enough. Any question about that? You may choose to do it another way. I just kind of choose to do these 2 and then slide them, translate them left or right. Okay, let's keep going here. Am I okay in saying that most of this is review? You've seen this stuff, maybe not yesterday, but you've seen it fairly recently. And okay, that's good. The next piece is the algebra of functions. This is probably the easiest thing we'll look at today. If we want to add the f plus the g of x, we simply add the whole f of x to the entire g of x. Whether it's a picture or a list of points or whatever it is, we just add them up, add up the y values. The f minus the g is the entire f of x minus the entire g of x, and so on. F times the g, we multiply the 2 functions. F divided by the g, we divide the 2 functions. And there's really only one kind of tricky thing about the algebra of functions, and that is the domain is always the intersection of the domains, because you've got to be able to take the f of it and the g of it to take the f of x plus the g of x. You got to be able to add them together, so you got to have the f and the g both. So it's got to be the intersection of the domains, with the exception of f divided by g. So g ends up in the bottom. We possibly might have a new restriction there because we can't divide by 0. Okay, just one simple example here. Not that this by itself is tough, but I want to contrast it with the composition of functions. So there's our two functions. We want to come up with another function that is the f plus the g function. So it is, by definition, the f of x plus the g of x. So the f plus the g ought to be that. And we just add them up, right? We've got a new function. Add up the like terms. 5x minus 3. Now let's look at it in terms of points, because we don't always have a function that's listed. Let's say that we've got the, well, let me leave that one there, and let's go to one that is the same thing, but we're adding up specific y values. So let's say the f is this is probably overly simplified here, but it does review one thing, is that we've got to have an intersection in the domains, which we do. Can we take the f plus the g of 1? Well, we can, because we have the f of 1 and we also have the g of 1, right?
Mm-hmm.
So what's the f of 1? It's 3. What's the g of 1? It's 4. So what's the f plus the g of 1? It's 7. So we've got basically 3 sets going on here. We've got the f set, which has 1 paired with 3, the g set, which has 1 paired with 4, and this third set, the f plus the g set, which has 1 paired with 7. Add the y values, right? Now, I specifically did this.
Sir,
Whoops. Can we take question? Yes.
sir, I didn't get the G of 1, sir. It
The
should
g
be
of 1 says we
of
look in
1.
the g set of points. The g of 1, the y value paired with the x value 1 under the g relation is 4. So the g of 1 is 4. Now, I'm not saying it's that. It's. I can't even see that, to be honest with you, on the other side of the screen. So I'm just making up some points. How about the f plus the g of 2? Well, that could be, if it's possible, if I can write, the f of 2 plus the g of 2. Well, we got a little problem there, don't we? We've got an f of 2, but we don't have a g of 2. So when this says you've got to have an intersection of the domains, we don't have. 2 is not in the domain down here. So you can only define the algebra of functions in values which are in both sets, the domain of both sets. So we don't have a g of 2, so we can't tell what the f plus the g of 2 is. And then the only additional restriction is that g of x can't be 0. Whatever we throw in the denominator it probably wasn't in the denominator originally, so it wasn't restricted in that fashion. Now we throw it in the denominator, it's got a new restriction. Okay, so that's algebra. Adding, subtracting, multiplying, and dividing functions. And the last little animal here is a composition of functions. Very different from the algebra of functions. So the f of the g would be how I would read that. And in fact, that really more or less describes what we're supposed to do. That we take the g of x first, do whatever that says to do, and then once we're done with that, we throw that result back into the variable position of the f function. So let's take a simple one. Let's say there's the f of x. There's the g of x. Let's start simple with a point. Let's say we want the f of the g of 1. So we want the f of the g of 1. So we start with the g of 1. What's the g of 1?
1.
Okay, we throw 1 in the variable position of the g function. So we double 1 and subtract 1. That's 1. Now that we're through taking the g of 1, we throw that final answer into the variable position of the f function, which means we put it right here. So 5 1s plus 3 is 8. Okay? Is that all right? I'm going to erase that because I'm running out of room down here. Now let's kind of leave it open that we're not going to go with a specific value. We're going to go with some generic x. The f of the g of x is exactly that. The f of what? The g of x. What's the g of x? Okay, we're doubling x. Now how do we take the f of something like that? Okay, take that whole mass, and to take the f of something, you put that something in this position, right? So instead of multiplying x by 5, we multiply 2x minus 1 by 5, and then add 3. Does that sound familiar? I'm hoping. Whoops. Yeah. So that's applying the f function to the results of the g of x, which means multiply the result by 5 and add 3 to it. So the end result is what? 10x minus 2? So we have a new function, a completely new function. It's not the sum, difference, product, or quotient of the original two. It's a composed function, the f of the g. Would you expect the g of the f to be the same thing? Now, it's a rare situation when they are the same, right? So the g of the f now, if it were addition, we would expect it to be commutative. So we're trying to commute the order and see what happens with the result. So the g of the f of x says we're going to take the f of x first. You'll have to tell me, since I can't see it, what's the f of x over there?
5x plus 3.
And how do we take the g of something?
5x plus 3.
2 times.
Okay, we're going to double it. Whatever we're taking the g of, we're going to double it and then do what to it?
Subtract 1.
Subtract 1, so we're going to double that entire mass and then subtract 1. So 10x plus 6 minus 1 plus 5. So let me go back to my earlier question. Is the f of the g the same as the g of the f?
No.
Not commutative, right? When you commute the order, don't expect the same result. Any questions about this? I'm going to erase this. Do another one over here. Just try to leave that one up over there. Actually, I want to do two more things before we leave that. Let's say under the f, let's get a couple of points over here. What are we doing with the f? 5x plus 3? So the f of 1 would give us what?
8.
8? And there are some other points here. I'm just going to leave that alone right now. What do you get when you put 8 into the g function? 15?
Yeah.
And again, there are some other points here. Bunches of points on both of them. Everybody agree, though, that these are 2 points on the 2 different functions? Okay, do we have enough here to figure out the f of the g of something or the g of the f of something? Well, let's go this way. We went the f of the g of something. Wouldn't we first have to take the g of that something? Well, we don't have a big long list of what we have the g of. What do we have the g of? 8. That's it. So we could take, possibly, we could take the f of the g of 8. At least we could start it. What's the g of 8? 15? Do we have the f of 15? Well, we don't in this list right now, right? Can we work the other way? Well, the only thing we have the f of is 1. Can we take the g of the f of 1 with this short list that we have? What's the f of 1? 8. And what's the g of 8? 15. So the g of the f of 1 is 15. So we have a third set of points here. Which, what did we start with? 1. And we put it through this little composition of functions, and we started with 1 and we ended with 15. And there are certainly other points in that. So 1 leads us to 8, 8 leads us to 15, right? So let's talk about the domain of a composed function, and then we can leave this alone. And there's still one other thing we need to do here, I'm sorry, but one thing with this one. Then we'll move to the other board. To take the g of the f of something, don't we first have to be able to take the f of it? Right? So it's got to be in the domain of f. Right? And then that result, this f of 1, that result, the corresponding element from the domain here, so the matching element in the range from the f of 1 has to be in the domain of g, doesn't it? It's not as simple as the algebra of functions. The domain, you kind of have to track it to see. You've got to be able to take the f of it, find that corresponding element. That corresponding element has to be in the domain of g in order to get a response. So it's always basically starting with the domain of the second function. That's what we start with, and we track it from there. Okay, I'm going to erase these, but I want you to tell me what they were if you wrote them down, because I want to use them again. Is this possible? Is it possible to actually write them down where they can be seen? Can you compose a function with itself? The f of the f? Well, let's try it out and see. What was the f? Golly. So we're going to take the f of x. So let's take the f of x first. Okay, I'm going to switch over here to this. It's just not working very well. Sorry. Okay, inside parentheses, the f of x. What is it?
5x plus 3.
And how do we take the f of 5x plus 3? Put this whole thing into the variable position, right? So instead of 5x plus 3, it's 5 of 5x plus 3 plus 3. Does that make sense? So we can compose a function with itself. What do we get out of that? Plus 18. So there's a new function, very different from the function itself, that is composed with itself. Let's suppose we had 3 functions. Is that possible? Or is this just binary? F of g, g of f, g of g, that's it? I think this would work, wouldn't it? You'd have to take the what? Tell me how to go about this. H of x first. Do what with that?
G.
Put that in the g, and then do what with that? Put that result into the f. So, and you can compose an unlimited amount of functions in this fashion. Now, that's hard to track domains when you do this. You've got to be able to take the h of it. That value has to be in the domain of g. Then take the g of it. That value has to be in the domain of f. So that's kind of difficult to track when you're doing a composition in that fashion. I said about 5 minutes, so we've got about 5 minutes. If you've got questions from section 1.2, I've kind of given you a boatload of problems, but there's a lot of good problems in these sections. I'm going to give you another boatload of problems today, but it's just kind of hard when I'm looking through there to narrow it down to just a couple. Here's the kind of problem you're going to ask me to do here. Let me, while you're looking. Let's suppose that you have some h of x. Can you write that as the composition of 2 functions? So now we're going backwards. Instead of being given 2 functions to compose, here's the final result. What 2 functions could have gone together to compose into this one? So I think it's a good thing to look at mathematics problems in 2 directions. And here's an example of that. Give me an f of x and a g of x such that I could compose them in some fashion, f of g or g of f, and come up with this h of x.
F of x could be x cubed,
I like that.
and g of x could be 2x plus 1.
Okay? Are you liking that?
Mm-hmm.
I'm liking that. Now, what order? You want f of g or g of f?
F of g.
F of g. Everybody agree? That's going to work? Now, can you see the two functions there in the composition? There is a you're cubing something, right? Now, you don't cube first. What do you do first? Don't you do something else before you cube? And isn't that the other function? Don't you double x and add 1 first? There's one of the things you want to do. And then after you've done that, you want to take that result and cube it. Now, some of you expressed the first day that you've had some calculus. Are we going to deal with composed functions in calculus? Remember a rule called the chain rule, where you've got to worry about the function inside and the function outside as well. So it will be to our advantage to feel comfortable with composed functions, because in dealing with the chain rule, we're going to be dealing with composition of functions. Anybody question over 1.1 problem set or 1.2 problem set? Any specific?
Could we go over number 12 and 1.2?
1.2, number 12. Okay, you might want to read these problems through because you don't always know what the relationship that's expected. This is page 36. This is section 1.2, number 12.
Yeah.
Let's read it through. The monthly cost of driving a car depends on the number of miles driven. Lynn found that in May it cost her $380 to drive 480 miles, and in June it cost her $460 to drive 800 miles. So we still don't know what the function is, per se. Express the monthly cost, C, as a function of the distance driven, D. Here we go. This is what we need. Assuming that a linear relationship gives a suitable model. Okay? So we're going to be dealing with a line. So we want monthly cost, C, as a function of distance. So we want C to be some function of D. Now, typically, we have y as a function of x, right? If you want to use that framework for slopes and, general equations, that's fine. So we want our ordered pairs to be of the form what? D. D is the independent variable. We're going to plug D into the function and generate C, which is cost, the dependent variable. So let's put our ordered pairs in that fashion. What's the first ordered pair?
480 and 380.
480 is distance. And what's the corresponding cost? 380. Might put that there just to remind us that's cost. What's the second ordered pair?
800.
800
460.
is distance. And cost is 460. Everybody all right with those? Express the monthly cost as a function of the distance. Well, what do we need to generate then? Slope. So over here, slope is what? Difference of y's over difference of x's. So what's slope going to be for us? Everybody all right with that? Okay. Cost difference, doesn't matter where we start as long as we're consistent. Let's start here. 460 minus 380 over difference of the distances. So we come back here to this same ordered pair. There's our slope. What do we get in the top? 80. And in the bottom? Okay. So reduced by 10. 8 over 32 is 1/4. Got a slope of 1/4. And back over here to our old friend here. There's our point slope, right? So our new point slope is going to be what? C minus C1 equals slope times D minus D1. Doesn't matter which point we choose, but that ought to work. C is kind of the general C. C1, which one do you want? Doesn't matter, does it? 380. M is 1/4. D minus, what's D1? 480. We want the corresponding D that goes along with this C. Okay, simplification of that be all right? Everybody feel comfortable with that? What else do we have here? Use Part A to predict the cost of driving 1,500 miles per month. So what are they handing us, and what are they asking for? They're handing us a D, right? They want to know the corresponding C. So we could take 1,500 and plug it in right here. Everybody all right with that? Draw a graph of the linear function. What does the slope represent? Well, what is slope in this case? What is in the numerator? Isn't that dollars? Right? Cost minus cost is dollars. And what do we have down here? Distance, which is miles, right? So would it be okay to say the ratio there is dollars per mile, right? $1 per 4 miles, or 1/4 of a dollar per mile, if you want to think of it that way. What does the y-intercept represent? What does it represent?
How much it costs just to have the car, not if you don't drive
Right.
it miles.
Driving 0 miles, right? D would be 0. So when D is 0, remember the D's are X's, right? So when D is 0, that's like a y-intercept, X is 0. So what does it cost you to have a car? Why does a linear function give a suitable model in this situation? Well, what do you think?
Two variables like your variables.
So the suitability of cost and distance, when you drive more miles, it costs more money, right? Seems like there's kind of a nice little progression. They plot along somewhat predictably, right? For every $1, you're going to go 4 miles. So that's it seems like it's well suited for a linear relationship. All right, well, we had time to go through one problem. How about that? Let me put some problems up here from 1.3 that you should take a look at. We can, if you still have questions, hang on to your questions, and we'll have time eventually to go through them. I'm taking this, I kind of pried a question out of you today that you're not having many questions, which is a good thing, but if you have them, we're going to make time for them somehow.